voice recognition, self-driving cars, companies that know you better than you know yourself. These are incredible technological feats that are all starting to come to fruition with the help of something called deep learning. My name is Matthew Drinovich, and I have been working with Professor Kevin Landon here at the University of Notre Dame this summer on using deep neural networks to analyze collisions in high-energy physics. Deep learning is an approach modeled after the human brain for gifting computers with the ability to think critically. This allows the computer to decide for itself what is important in a set of data, so they can separate two similar events, such as a dog from a cat. In particle physics, distinguishing two events is particularly difficult. In the CMS experiment at CERN, protons are collided at nearly the speed of light, and for a split second convert that energy into more massive particles, and then these particles rapidly decay. Due to the nature of quantum physics, any outcome could be the result of any of several different starting points, and distinguishing a Nobel Prize-winning collision from a common one can be quite challenging. My research focuses on developing deep learning models to isolate rare and indistinguishable events, specifically those that produce a Higgs boson and two top quarks. Now, in an ideal world, after a collision, we'd be able to reconstruct this diagram. However, in the real world, things are not so simple, and after collision, this is about all the data we get. And we have to be able to guess how the puzzle pieces fit back together to reconstruct the original diagram. When we gave a deep learning model this ideal data, it was able to correctly identify an event 87% of the time, which is better than current statistical measures. However, when we gave the model real data, it was only able to correctly identify events 70% of the time. My research has since been focusing on developing models that might bridge the gap between the ideal model and the realistic model. One model, termed SuperNet, uses the ideal model at its core, but works with real data by looking at every possible combination of the puzzle before making its decision. Here we can see SuperNet learning to separate the important events, which are the green bars, from the common ones, which are the blue bars. Now, ideally, SuperNet would be able to push all the green bars to the right side and all the blue bars to the left side. Now, SuperNet's not quite there yet, but we hope to continue to refine it and potentially reach accuracies comparable to the ideal model, so that researchers might be able to identify the next Nobel Prize-winning collision. Thank you.